everyone. Welcome into lecture number 9 of linear algebra. Today's lecture is on row and column spaces of a matrix. So let's start off by let's start with the row space, and then I'll leave it as an exercise for you to define the column space, but I think you'll see how it goes. So let's suppose that A is an m by n matrix, and we'll do this for real matrices, but again, almost everything that we do for real matrices extends to complex matrices. We haven't really studied those much yet, so let's stick with real matrices for the sake of today's lecture. The subspace, this is what we're defining here. So the subspace of R, and I'll write this as 1 by n, but remember R1 by n is essentially just the same as Rn, except that these are row vectors, right? 1 by n makes a row vector. And so the subspace of this space that is spanned by the rows of A, all right. Remember, the rows of A are denoted by, I'll write them in set form here, but A1, we put these with little arrow hats on them, A2, etc., and there are m of these that live in R1 by n. So the subspace of R1 by n spanned by these m vectors, this is called the row space of A. All right, and remember, any span is a subspace, right? So it's called the row space of our matrix A. All right, and we denote this by, so we write just row of A, or sometimes just R of A if it's clear what we mean by R here. R could mean different things, right? It could mean range, it could mean row, it could mean other things that I'm not thinking of right away, but it's a little dangerous to write R of A if there's no context, right? So I'm probably going to write row of A like this. If you know exactly what you're doing, you can write R of A and just be careful to make sure that R is obviously referring to row and not to something like range. But this is defined to be the span of those row vectors that make up the matrix A. All right, so that's the row space of our matrix A. How do you think we're going to define the column space now? So I'm going to write this. I said I would leave this as kind of like an exercise, but we'll write it out. Similarly, I'm going to write the following, right? So I'm just going to write the definition like this. So col of A, again, you probably would never write just C of A. You could, but I don't recommend it. So I recommend just writing row and col for these spaces. But col A, this is the column space of A. This is the span of the columns, right? So remember, our matrix A, if it's m by n, it has m rows that are in R1 by n, and it has n columns that live in Rm by 1, or just Rm, right? So this is going to be the span of the columns A1, A2, etc. up to AN. So remember, columns just get the bar and rows get the arrow. That's the convention that we've set because we don't have boldface pen here, right? But this is a subspace of Rm by 1, which is, Rm by 1, we can just write Rm. Because remember, our default is column vectors. So let's look at a very simple example, and then we'll talk about some theorems and some consequences of these definitions, and geometrically, what do these two spaces mean? We'll also define another space as we move forward. But here's a very, very simple example. So 1, 0, 0, 1, 0, 0. This matrix has 2 rows and 3 columns. So this A is in R2 by 3, 2 rows and 3 columns. All right, and let's write down the row space and the column space. So now that we've talked about bases and dimension and linear independence, etc., spanning sets, then we can define our subspaces just by giving a basis of those subspaces, right? So I think it's pretty clear here that for the column space, let's start with the column space. The column space is going to be spanned by these two vectors. They are linearly independent just by looking at them. I mean, you can check if you want by taking a smaller matrix and taking the determinant to show that they form a basis of the column space. And this vector is the 0 vector, right? So that's never going to be part of a basis. So we can write down then that the column space of A is the span, for this example, right, is the span of these two vectors, 1, 0, and 0, 1. And then when you think about this a little bit more, actually these two column vectors form an entire basis for R2, right? And so the column space of A is all of R2 actually. So the entirety of R2 for the column space of A. All right, what about the row space? So the row space, there's only 2 rows. So let me switch back to my highlighter and choose some different colors. But the row space is going to be spanned by this row and by this row. They're the only 2 choices, but they are linearly independent. You can see as far as the rows go, this was a very simple example. So there's only a 1 entry here and nothing here. Same thing here. So there's no way that these could be linearly dependent, these 2 rows. And so the row space of A is going to be the span of these 2 vectors, but these 2 vectors live in 3-dimensional space, right? So the row space, I'm going to write these as vertical vectors, 1, 0, 0, and 0, 1, 0. All right, so this is a subspace of R3, but it is not all of R3. So notice that this space does not fill out all of R3, while the column space does equal all of R2. And part of that is because of the dimension of the matrix, right? It's not a square matrix. It's a 2 by 3 matrix to start with. And then also part of that is just the entries, right? Because if these 2 rows were exactly the same, then actually there would only be 1 basis vector down here in our spanning set. Okay? So we'll get into this deeper as we move forward, and let's start that by talking about a theorem now. So this theorem is a theorem about row equivalent matrices, and so one of the questions we might have is, okay, well, this was a very simple example up here of how to find the row space and the column space of this matrix, or bases of those spaces. But what if it's more complicated, right? What if these entries are more difficult to just look at, or if the matrix is much bigger? And so we'll start with a theorem here. And this one says that 2 row equivalent matrices have the same row space. All right. So we want to sketch the proof of this. We want to make sure we believe this, right? So let's sketch the proof. So what are we going to do? Well, we start with 2 row equivalent matrices, right? So let's let A and B be row equivalent matrices. And they can be in any dimension, right? Because we know what row equivalent means. It means that they can be made to be equal by multiplying one of them by a series, finite series, of elementary matrices, right? Which are always square matrices. So let A and B be row equivalent, not spelled right, but equivalent matrices in R, let's call this M by N. All right, and we want to show that they have the same row space. Well, how do we do that? Well, so the idea here is to show, and we're not going to do the whole thing, that's why I wrote sketch here, but the idea is to show that the row space of A is a subspace of the row space of B, and similarly that the row space of B is a subspace of the row space of A. Remember, this less than or equal to symbol means not just a subset but a subspace. And so if these are subspaces of each other, then we conclude, right, then they must be equal to each other. Because if 2 vector spaces are subspaces of each other, they have to be the same vector space. All right, so let's just do one direction here, and then you'll see, I think you'll see exactly how the other direction goes. And again, I'm not going to write out all the details, but I'm going to sketch it here. So let's say this. If B is row equivalent to A, I'm going to write this RE, row equivalent to A, then what does this mean? This means that the row vectors of B must be linear combinations of the row vectors of A. So we have the rows of B must be linear combinations of the rows of A. And this is just by definition, right? Because B is a product of some matrix, some non-singular matrix M, made up of elementary matrices, times A. So when you multiply this all out, you get that the rows of B are linear combinations of the rows of A. And therefore, just by definition, right, therefore, the row space of B is a subspace of the row space of A. Because every row in B is made out of a linear combination of rows in A. All right? So you can make the same argument So the reverse argument is also true. You can make the same argument starting with A and thinking of B. And you can fill in some details here. So it's a recommended exercise to fill in the details here and make sure that you fully understand exactly how this works. But at the end of the day, once you do fill in those details, we'll have this theorem then that two row equivalent matrices have the same row space. All right, and so this gives us an idea of how we can actually determine a basis for the row space of a matrix. So let's do it. So here's an example. I'll give you a hint of how to do it, and then we'll do this example here. Let's consider this matrix A equal to, so I'm just going to give us a matrix here, 1, 2, 1 for the first column, -2, -5, -4 in the second column, 3, 1, -7 in the third column. All right. What I would like to do is I want you guys to find the RREF. So use, or just REF. We just need to use REF. So basically find the LU factorization. So use REF to find an upper triangular. All right, upper triangular matrix U that is row equivalent to A, and then use this to find a basis for the row space of A. And if you want, you can think about the column space, but start with the row space, and when you come back, we'll talk about the column space a little bit of this same matrix. So take a minute, work on this, and I'll see you guys in a few minutes. All right, now that you've had a chance to work on this, let's see how you did. I'm just going to write down the upper triangular matrix, so hopefully you guys got this. But by using the REF method, I got that the upper triangular matrix should be 1, 0, 0 for the first column, -2, 1, 0 for the second column, and then 3, 5, 0 for the third column. And this was obtained using only, so REF, row echelon form, right? So it was obtained using only row operations. And so therefore, the row space of U is the same as the row space of A. So the row space of U equals the row space of A by our theorem, right? By the theorem from number 2 up here that we just wrote down. So therefore, we have a basis, right? We can just use these vectors as a basis, and we see that this third vector down here of all zeros, that's never going to be included in a basis, right? So we can say then thus a basis for row of A, this row space of A, is given by just the first two rows, right? So 1, -2, 3, and you can do transpose if you want here. I like to write these as columns, but you can write these as rows if you want. And then 0, 1, 5. But there's a basis for our row space of not only U, but also A. And again, that comes from our theorem. Now, if you thought about the column space, then the same is not true. So this theorem doesn't say anything about the column spaces being equivalent after we've done row equivalent, right? Row operations. So row operations are definitely going to change the column space. And we can see that just by looking at these two matrices. So all of the columns of A have entries in the third row, right? But none of the columns of U have entries in the third row. So there's no way that the column spaces of U and A are the same, right? So it's impossible. You can see just by looking at it. There's no way to get entries in the third column, in the third row, the third entry, using the columns of U. So the column space of A is not equal to the column space of U. All right, so that is, we're going to talk about this again in the future here, but yeah, so we'll come back to this idea in a minute, but the column space of A is not the same as the column space of U, and you can see that just by comparing, right? So we'll leave it there, and then we'll come back to this idea in a few minutes and talk about what we can actually do there to find our column space. First, we want to give another definition. So this is definition. We'll call this number 4. So this one says the rank of a matrix, this is the thing that we're defining now, the rank of a matrix, this matrix A is in Rm by n. This is the dimension of the row space, and so it's defined to be the dimension of the row space. So we write this as RK, or you can just write out the word rank if you want, rank of A, or lowercase r, again, if you're careful. So sometimes notation can be too short and too sweet, right? So, but if you understand what you're working on here, then lowercase r would mean rank in this context. I would like to always at least put the K here, but this is defined to be the dimension of the row space of A. All right, so remember what dimension means. That's the number of vectors in a basis, right? In any basis. And so what we found up here then is that the rank of this matrix A is 2, right? Because there are 2 basis vectors, 2 linearly independent rows in this matrix A. So the rank of A is the number of linearly independent rows in A. The dimension of the row space. All right, so there's a definition. Here's a theorem, and again, I'm going to write this now, but we will talk about this later on, and maybe leave the proof as an exercise. But here's the theorem, though. So if A is an m by n matrix, then it turns out that the dimension of the column space of A is equal to the dimension of the row space of A. So the row space and the column space have to have the same dimension, and therefore, by the way, the rank is defined to be the dimension of the row space, but this must be the same number, right? The dimension of the column space must also be the rank. All right, so the proof of this one is going to be an exercise, but it's going to happen later. Okay, for now we'll just believe this. And now what we can do is we can go back to our previous answer, right? And so we see, all right, so the dimension of the column space is the same as the rank of A. So that means up here, the rank of this matrix was 2. So there's 2 linearly independent columns. Looking at our matrix U, right, the one that we use the row operations on, we can see that the first and the second column of this matrix are linearly independent, or the first and the third, or even the second and the third, it turns out. But just very clearly, though, because of the leading ones, we can see that the first and the second columns are linearly independent. However, we already talked about you cannot use these vectors, right, as a basis of your column space because there's no way to get the vectors back from the actual matrix A. So instead, what we can do is we can say, all right, column 1 of matrix U and column 2 of matrix U are linearly independent. These matrices are row equivalent. They have the same row space, and their columns are therefore related, but they're not, the column spaces are not equal to each other. But otherwise, the matrices are related to each other, right? And so it turns out what we have to do is we have to go back to our original matrix A and say, actually, what this is telling us is that columns 1 and 2 are linearly independent. They're going to form a basis of our column space, but it's not columns 1 and 2 of the matrix U. It's columns 1 and 2 of the original matrix A over here. All right, and so we go back and we can write, all right, after some work here, the column space of A is equal to the span of the first and second column. So we learned this by using the upper triangular form here, or the row echelon form, but it's not these ones, right? It's these ones. So it's the first and second columns of the original matrix. So it's the vector 1, 2, 1, and then the column vector -2, -5, -4. And those are going to form a basis for our column space. All right, and it kind of stems from this theorem here that the rank is the same of the column space and the row space, and it also stems from just some facts about row operations and what row operations actually preserve. So they preserve the row space, they change the column space, but they don't change the independence of the columns. Okay, so we can just take that for granted right now, and we'll prove that later on in the semester as we move forward. All right, so let's leave that there for now. So now we know we have this notion of rank. we should write this down actually before I go too much further. But we have found this example, right? We found bases for the row space and the column space, and both of them have 2 vectors. So the rank of this matrix A is 2, right? It's the number of linearly independent rows by definition, and by the theorem, it's also the number of linearly independent columns of A. All right. Well, let's consider the following situation now. So let's suppose we have a system of equations, a linear system of equations. So consider a system of equations with a matrix equation of the following form. So a system of equations, let's just write it this way. A times x equals b. All right. And we can do the following. So if we write our matrix A as a row vector of its columns, we've done this before, but as a row vector of its columns, so A1, A2 through AN. Now, each of these A sub I live in R, these are in Rm by 1, right? So they're in Rm, they're column vectors. And similarly, our vector X is going to live in Rn. It's got n entries. And our vector B is also in Rm, right? We can write out what it equals here if we want. It's not super important for this portion, but for these two, it is important that we write them this way. So B1, B2 through Bm, this is a vector in Rm, right? And X is in Rn. If we multiply this out on the left-hand side, look what we get, right? So A times X is then equal to this row vector whose entries are column vectors, we should remember this, times this column vector whose entries are just real numbers. And when we multiply these together, we can write this as x1, a1, plus x2 number times a2 vector through xn, an, right? And our system of equations says, all right, well, the equation we're trying to solve is we're trying to find these x values such that this sum, this linear combination of the columns of A, equals B, right? Equals B. And so we arrive at this theorem, actually, just by looking at this. Just by rewriting this, we get the following theorem, almost without proof. I mean, this is kind of the proof, just unpacking the definition of what the system of equations is telling us. All right, it says the following. The system of equations, the system AX equals B, is consistent. Remember, consistent means that it has at least one solution, right? But it's going to be consistent if and only if the vector B is a linear combination of the columns of A. So if and only if B can be written as a linear combination of the columns of A, or in our new lingo, we could say then that B has to be in the column space of A, right? So if B is in the column space of A, then our system has a solution. If B is not in the column space of A, then our system has no solution. There's no way to build our right-hand side vector, our vector B, as a linear combination of the columns of A if it's not in the column space to begin with. All right? So that's the idea here. And we get a corollary from this as well. And the corollary says that A in Rm by n is non-singular. Remember, that means that this should be n by n, sorry. Non-singular is for square matrices only. So for a square system, is in Rm by n, is non-singular if and only if A, what was going to write is fine, but here's what I really want to write here, because I want this to be in the language of our column spaces. So if and only if the column space of A is equal to all of Rn. Okay, so if it's equal to all of Rn. And so where does this come from? So let's just sketch kind of the proof of the corollary here. So recall that one of the criteria for singularity or non-singularity of a matrix is the following. So A is non-singular if and only if this system, A times x equals 0, has only the trivial solution. Right? Has only the trivial solution. And the trivial solution then means that x is equal to 0. So if we write this out in the context of what we just did on this previous example here, right? If all the x's are 0, then what does this tell us, right? So then it tells us that the following is a criteria for non-singularity, right? That x1 a1 plus x2 a2 plus all the way through xn an equals 0 implies that all these x's are equal to 0, right? So if this is true, what does that mean? Well, that's the definition of linear independence, right? So in this scenario, in this case, the columns A1 through AN are linearly independent. There are n of them in n-dimensional space, right? And therefore, they must span the whole space. They must form a basis, right? And so thus, they must form a basis for Rn. They're also the columns of A, right? And so just by unpacking all these different definitions, in this case, the column space of A is equal to all of Rn because the columns form a basis for Rn. All right, so again, it's just a matter of unpacking definitions. It's not like some crazy proof where you have to have some great insight that only comes to the, the most brilliant mathematicians who ever lived. But it does sometimes take some time to just sit down and think quietly, carefully, think about exactly what the definitions mean, right, before you fully understand exactly what the theorem's saying. So please take the time to think this through, make sure you understand the arguments, pause the video if you need to, rewind the video if you need to, and just make sure that you understand what this is saying, because it is important, right, that if A is non-singular, then its column space is all of Rn. And by the way, based on our theorem up here, that also means, so that would mean that the rank is n, right? So therefore, the row space is also all of Rn in that case. Okay, so as we move forward here, that's the theorems. We're going to get to some examples. I got one example, but before we do so, we need to make one more definition. So here's our next definition. And we've seen this in our previous studies, but we're gonna reframe it now in the context of the row and the column spaces. For this one, again, let's let A go back to being just a rectangular matrix. It doesn't have to be square. So let's say A is in Rm by n. All right. The null space of A, so this is kind of a reminder, but the null space of A, this is the set of all x. So it's a set of all x in Rn. So Rn, n by 1, right? But Rn, we'll just say, such that, so it's the set of all solutions of the homogeneous equation, basically, but we'll write it this way, such that A times x is equal to 0. And so we denote this space, it's called the null space, right? So we denote this space by just capital N of A. So this is the null space, denoted by capital N of A, and it's the set of all solutions of this homogeneous equation, right? And depending on the dimensions of the matrix itself, we have theorems about consistency theorems, right? About the minimum size of this null space, the maximum size, etc. But let me draw a picture here real quick, and then we'll get to the point of why we're reviewing this right now. But let's suppose that this is Rn, and over here, draw another set of axes. This is Rm. The way I've drawn it, it looks like this is three-dimensional space and this is two-dimensional, but that's not the idea here. The point is that they're different, okay? Just that they're different. Now, they're a matrix that is an m by n matrix in multiplying by vectors, right? So a matrix that is m by n, it multiplies by vectors in Rn, and it spits out vectors in Rm. So it can be thought of as a function, okay? And when we get to the next chapter in this course, we're going to focus a lot on this idea of matrices as functions. Right now, let's just lay the groundwork for it, though. So the idea is if we take a vector over here in Rn, right? So this is our x, lives in Rn. We multiply it by the m by n matrix. It's going to spit out a vector over here that lives in Rm, right? So this is our a times x. All right, so that's A times X. And now, here's how this works. The domain of this that spits out all these vectors, okay? So that gives us, so for, let's say, for example, all the vectors in the column space live over here. So let's say this is the column space of A. They live in a subspace. So I'm going to draw this as a one-dimensional subspace just because of, again, the choice that I've made here to write this, to draw this so it looks like two-dimensional space. But let's say this is the column space of A, and that all the vectors which map to the column space come from the row space over here. So this is supposed to be now a plane. All right, so this over here is supposed to be the row space of A. This is a plane of vectors that obviously contains the origin, right? Goes through the origin because this one has origin over here. And it maps all these vectors that live in this plane, the row space of A, to all the vectors in the column space over here. All right, but there is potentially, these have to have the same dimension though, so my picture does not look right. So our theorem said that they have the same, the row space and the column space have the same dimension. So, and it's true. It's not just our theorem saying it, it's true. So here, this will be the row space. Again, it's weird because of the way I decided to draw this. But there, we'll call that one the row space then. So the matrix takes this and all the vectors that live on this line in Rn dimensional space and maps them to all the vectors that live on this line in M dimensional space. And it includes, it takes the zero vector to the zero vector, right? That's always a solution, trivial solution. The question is, what happens to the rest of the vectors though? So if this is a line in space, so there is then a plane that is geometrically orthogonal to this entire line, right? So this is not a geometry class, but there is a lot of geometry involved in linear algebra, right? But this plane right here, all the vectors in this plane, because the dimensions of the row space and the column space have to be equal, all these vectors have to get sent to here, right to the zero vector, right? And so every vector that lives in this space gets sent to the zero vector. So this is what the null space looks like. The null space is all the vectors over here that don't live in the row space, okay? All the vectors that don't live in the row space, the matrix maps all of them by multiplication to the zero vector in Rm. All right, and so that's the idea here. So that's geometrically the idea, but let's write down a couple more things here. So number one, the null space is always going to be a subspace. So N of A is a subspace of Rn, always, of Rn. So remember, the matrix is Rm by n, and it maps Rn to Rm if we think of it as a function like this. So we multiply x, we get Ax over here, right? So it's a subspace of Rn, and the dimension of the null space gets a name. So the dimension of the row space is the rank, right? The dimension of the row space is the rank, and the dimension of the null space of A, this is called the nullity of A. All right, and so this is denoted by lowercase null of A, and that is, again, the dimension of N of A. Dimension of the null space. All right, and so this leads us to a theorem, and if we believe the picture that I've drawn, the correct picture here that I've drawn, then what we get is the following theorem. So the row space is in kind of one direction, the null space is orthogonal in this other direction, but these kind of add up to the whole space. So here's the theorem. If A is an m by n matrix, then the rank of A plus the nullity of A is always equal to n. Okay, so that is a theorem, and it's a very important theorem. It's called the rank nullity theorem. And we will use this quite a bit moving forward. All right, so there's our rank nullity theorem. So we've kind of justified it geometrically, maybe, more or less. Didn't prove it. The proof is in the text, is recommended exercise to at least read through it and make sure we understand how it works. But let's finish this lecture with an example. So this is item number 7. What I would like you guys to do is, given this matrix A, 1, 2, 1 in the first column again, 2, 4, 2 in the second column. This is going to be a 3 by 4. So -1, -3, 1, and then 1, 0, 5. Here's a matrix A. I want you to use the same method that we did on the previous example. So in other words, find the row echelon form of this matrix, and then use the row echelon form to find bases for the row space, null space, and column space. All right, so let me write this out. But use the REF form of A to find bases of all 3 major subspaces. So this is the row space of A, the null space of A, and the column space of A. Okay, so take a moment, work on that. Be very careful with the column space again. Remember what we talked about before. The null space, you're going to have to think about exactly how the row echelon form is going to help you with that. And then the row space is the easiest one, right? You just pick out the rows because the row echelon form preserves the row space. So take a moment, work on that, and then when we come together, we will finish off this lecture. Alright, so like in the last one, I am going to just write down the row echelon form of this matrix. So the upper triangular matrix that I get after row echelon, applying the row operations and getting this in row echelon form, is the matrix whose first row is 1, 2, 0, 3. Second row is 0, 0, 1, 2. And then the third row is all zeros. So hopefully you got the same thing here for the row echelon form. Now, how are we going to use this to find our bases? Well, remember the row space, that's the easiest one, right? So the basis of the row space. So the row of A, this is just going to be the span of these rows. So let's leave them as rows. So you can use the rows from U for this one. So 1, 2, 0, 3. And then same thing, the second row. We need this one, right? And then the third row is the 0 row, so we don't need that, right? So notice this wasn't asked, right? But the rank of A is going to be 2. There are 2 linearly independent rows. So the number of basis vectors in our basis, the number of vectors in our basis is 2 for the row space. So that's the row space. What about the column space? Well, the column space, we can, again, by row echelon form, just look for leading ones. So our leading ones are columns 1 and 3. Remember, these are not the vectors that we use to form the basis of our column space. We have to go back to the original matrix and pick out the columns that correspond to them, right? So columns 1 and 3 from the original matrix. So our column space of A is going to be spanned by columns 1 and 3, but columns 1 and 3 of A. So 1, 2, 1, and then -1, -3, 1. So there's a basis for our column space, right? Again, same number, there's 2 of them. All right, now what about the null space? Well, the null space is the set of all solutions to the equation AX equals 0, or because of the row operations preserve the row space that also preserves the null space, right? And so by preserving the null space, it means that we can solve this system right here, right? So this augmented, we can write down the augmented matrix. 1, 2, 0, 3, augment 0. 0, 0, 1, 2, 0, etc. Right? And so the solutions of this system will be if we can find a basis of solutions of this system, we will get the null space, right? We'll get a basis for the null space. We want to find the whole null space. So we want to find the whole solution set. That'll give us the null space, and then we can pick out our basis vectors. So let's look at these equations, right? This first one says that x1 plus 2x2 plus 0x3 plus 3x4 is equal to 0. And then this next one says, all right, well, x3, maybe we should move this a little bit, right? Just to line up all these variables and write this as a system of equations. But the next one here says that x3 plus 2x4 is equal to 0. And so we can solve these for x1 and x3 in terms of x2 and x4, right? So In other words, our x1 can be negative 2 x2 minus 3 x4, and our x3 can be negative 2 x4. And now x2 and x4 are free. So x2 we can set equal to alpha, x4 equal to beta. So these are our free variables, right? And so there's going to be our dimension right there, right? The dimension of the null space is the number of free variables. It's 2. Well, that's exactly what it should be, because the dimension of the row space is 2, right? And they both have to live in R4. And remember, they have to fill out all of R4. So that's exactly, we've got exactly the right number of free variables just by comparing. And then when we plug these in, right, then we get a formula here. So we'll see then that our solution is going to look like x equals, right? x1 is going to be negative 2 alpha minus 3 beta. x2 is just alpha. x3 is negative 2 beta. And x4 is just beta. And if we break this up, right, then look what we get. We get alpha times negative 2, 1, 0, 0, plus beta times negative 3, 0, negative 2, 1. And just by writing this out, just like we did at the very beginning of this semester, right, the very beginning, finding these linear combination of these solution vectors, we have found a basis of our null space. So it's not, that's not the only answer, but it is, we're just asked to find a basis. So the null space of A is spanned by, technically, we can leave these as columns, it doesn't matter. But they have to be in R4, right? So the vector is negative 2, 1, 0, 0, and then the vector negative 3, 0, negative 2, 1. And so there's our null space. Again, the rank of the null space is 2, so the nullity of A is equal to 2. Remember that the nullity plus the rank has to add up to the number of columns of A, right? The dimension of the ambient space where the row space lives. So in R4 in this case. So that's why they both equal 2. All right, well, let's leave this one here, and I'll talk to you guys in the next one.